It's my pleasure to introduce to you Professor Sylvia Serfaty, who currently holds a Silver Professorship at the Carroll Institute of Mathematical Sciences at New York University. And before that, she has worked in Paris at the University of Paris South and Pierre and Marie Curie University. And Professor Serfaty works in mathematical physics, analysis, and PDEs, and with some of her work, for example, including important contributions to the Ginzburg-Landau theory of superconductivity, and more recently to Coulomb-type systems. She has received the Prize of the European Mathematical Society in 2004 and the Henri Poincaré Prize for Mathematical Physics in 2012. And in 2018, she was a plenary speaker at the International Congress of Mathematicians in Rio. Recently, she has been elected a member of the American Academy of Arts and Sciences and the European Academy of Sciences. It's a great honor to have you here. Thank you so much. And over to you.
Okay, thank you very much for the invitation and the introduction. And so I tried to think of a topic that would be fun and suitable for undergrads. So I'm not going to talk very much about what's the core of my research interests related to physics, but something that's also related to some of my research from some years ago. But that could be, really something you can follow at the level of undergrad, and hopefully that would be a little bit fun. So it's about how certain games with one or two players and certain rules that I will try to describe can help to solve PDEs, and conversely, how PDEs can help to find best strategies for games. So this is a whole topic really of its own with this correspondence, or sometimes goes by the name control theory, optimal control, stochastic control, optimization, etc. And so I want to present it to you first in some very simple examples. Example one is going to be exit time from a domain. Okay, so you have a domain, a region of space. So here, let's think of the plane, and you're a unique player. Yeah? You start from a point X, and the question is, what is the minimal exit time starting from X if the rule is to move at velocity v of norm less than 1. Okay, so the answer to this is very easy. Of course, if you want to exit the domain, starting from X at velocity less than 1, you all know that you should follow a straight line going to the nearest point on the boundary if it exists, and basically to the projection of X to the boundary, and you should go straight at velocity 1 along this straight path. So that's not a surprise. So let's call U of X this minimal exit time with these rules. Then it's clear that I can identify the solution as being the distance from X to the boundary, so I call my domain point. Okay, but if I want to be a little bit more pedantic, I can rewrite my problem as saying, okay, I'm going to have a trajectory y depending on time. So X is for the starting point and Y is for the, and it's going to solve the ODE y dot equals alpha of t, where alpha is then the velocity, with constraint that the initial data is at X and that alpha is less than 1. So alpha will belong to this admissible set, which is basically the unit ball in the vectors. So it's functions that are valued. Okay, so this alpha now is called the control. And A is the admissible set of controls. So I have chosen something particular by choosing this unit ball. I could choose something else if I wanted, and I could rephrase the same problem. So now let's look at example 2. game of Paul and Carroll. So this game was invented by a colleague of mine from NYU Courant named Joel Spencer. And he invented it in connection with combinatorics questions. It was not for fun, it was really to solve a math problem. To solve combinatorics / theoretical computer science question. Combinatorics question. And so here is the game with its rules. So you have two players, Paul and Carroll, and there are adversaries. So two opposing players. We call them Paul and Carroll because Paul is for pusher and Carroll is for chooser for other reasons. And they are in the domain omega. So let's think for now of the plane, but we can imagine the same in higher dimension, but let's stick to the plane for now. And we start again from some point X. So now the players take turns. There are several rounds of the game. And so at each round, what happens is this. Paul chooses a vector V of norm 1. Not unlike the previous game. Second, Carroll chooses a number plus or minus 1. And then what happens is the game moves to position X plus epsilon BV, where epsilon is some small number that's given to you. Small, and which eventually will be sent to 0, as often is the fate of epsilons. And we repeat. Okay, so Paul chooses a vector. So actually the steps are very small because the steps are epsilon V. And then what Carroll can do is she can reverse his choice. And then you start again from there. And now, again, choose a vector, but maybe in fact you get sent there, etc. So you have to imagine this picture as a bit not to scale because the steps are very small. And what is the goal of the game? Is that Paul wants to exit as fast as possible, or in as few steps as possible. And Carroll, all she wants is to prevent that from happening. Okay, so Carroll wants to slow it down as much as possible. So either prevent it, or if she cannot, slow it down. And so now the question is, can Paul exit? In how many steps? What is his optimal strategy? How does he exit? Okay, so I'm gonna let you think a little bit about this if you're bored with the rest, and not give the answer right away of whether he can exit and how, to preserve a little bit of suspense. But so first of all, is the game clear? The rules of the game, you would be able to play it with your neighbor. And of course, you could think of extending this game to higher dimensions, but you would have to change the rules a little bit. Okay, so now I want to come back to the first type of games, which I want to recast in a more general framework. And of course, we're going to see that this game of Paul and Carroll and the exit time game are related to PDEs, even if it doesn't seem like that at first glance. So this is a more general framework for the first type of game. So we're going to have now again some trajectories where you're moving, and now the motion is going to be some general function. So just like an ODE, function of the position, but with possibly the dependence in a control. So alpha belonging to some admissible set is now called the control. So you have to define what is your admissible set. But now these things depend on alpha. And let's say you start the game from x at times little t. So it's not completely standard for this notation. It might seem a bit confusing, but in fact it is appropriate for reasons you will see later. Okay, so the general time is called s, and the initial time is called little t. And then at time capital T, so there is a final time, which is going to be bigger than little t, at which a clock rings, if you want. We terminate. And what do we collect at the end? So there is a sort of total capital earned along this game, or score collected, or if you prefer, you can decide on a cost. So of course, mathematicians like to minimize things, in which case you would like to think of a cost, you would like to minimize your cost, but economists like to maximize things. They want to maximize utility functions. But of course, up to reversing, changing your function into its opposite, it's all the same. So you decide whether you prefer to think of it as a cost or as a score, as a score that wants to be high. But anyway, this is the cost, C xt, the cost starting from x at time little t. If you make the choice of control alpha, so alpha is the whole trajectory of controls a long time, is going to be defined as something that gets integrated along the trajectory. So as you move, you collect a sum, an integral, which is a certain function. So this f here up there was given to you, and here in the same way, this little r is given to you. You decide what it is. And you integrate little r along the trajectory, and it's possibly a function of alpha as well. And also at the final time, you can have a bonus. So if it's a score, you're having a positive bonus, or here, if it's a cost, you're having a final time, a final price to pay. You pay something which is a function g of where you are at the final time. Okay, a function of the final position. So these types of things are actually quite relevant to things like economics or finance or engineering when you want to optimize something. So for example, try to think of your bank account, right? So you have a strategy which is how much money you're gonna try to invest every week or every month in your bank account. The amount of money you're gonna collect over your life is going to be a function of how much you're putting in every month, but also the interest rate. Maybe it's just going to grow exponentially with some interest rate. And maybe at the very end, maybe let's say you give away your money to your heirs. So they're gonna collect this, plus maybe some inheritance bonus, or maybe more likely a tax, a tax on inheritance. So this would be negative then, right? So what your heirs receive is something that's been collected all along your life, minus this final inheritance tax. So this is actually a completely realistic or semi-realistic, or at least relevant type of way of modeling for concrete problems. So it's not really about playing in the plane, like I make it sound like, but it's like that. Okay, so this is one type of game you want to play, and then of course what you want is to. So here I'm going to try to minimize this cost over the choice alpha, because after all, this is the only choice we have. And I'm going to define u of xt to be the minimum over alpha over all the choices of xt of alpha when starting from x at time t. And now there's something that's easy to say, is that if I start at time capital T, then the game doesn't have any time to be played. The clock rings right away, and so you don't collect anything. You just collect this final time bonus or cost, but the final position is the initial position. So you know it's g of x. It has to be g of x. There's a variant where instead of having a final time, you have a target in space. You have a g, a target in space. So you're trying to reach a certain set. You're trying, and you stop when you reach that set. So it's a bit like the exit time, or the exit time is a particular case of this, where big G was the boundary. That was big G, or the outside omega complement. So then you have a capital U of x will be the minimum of Cx. So now you don't have to say what's your initial time. You can call it 0. When Cx is the integral from 0 to the horizon time. So the time that you reach capital G. And the same thing, plus the little g. And now what's interesting is that this thing, this final position, will always belong to the target, big G, because that's the definition of. So now what we know is that big U of x is equal to big G of x if little x is in G. Because if you start in the target domain, you don't have to move at all. You finish and you collect little g of x. So maybe it's starting to look like to you like we're specifying here like an initial value problem, like some initial data for an equation. So it's actually not an initial data, it's a final data, because big T is the final time. It's a final time data, but up to reversing time, changing time, it's opposite. It's like an initial data problem. And this one is like a boundary value problem. Right? So this one is like final time data. And this one is boundary value data. So these two variants have this thing. One is a time-dependent function. The other one is a time-independent function. Okay, so the second one is the one that is a generalization of the exit time problem that I presented you first. Of course, now you just have to say that the cost is just the integral of 1 along the trajectory. You just pay a price proportional to the length of your trajectory, and G is the boundary, and it's exactly that game. So I've just generalized that game. Okay, so now let's see why this solves the PDE. Well, there is something that is called the principle of dynamic programming. Okay, so you give yourself a small time little h, right? Small. What I want to say, and this is the principle of dynamic programming, so let's write it. I'm going to write it in this time-dependent situation when I have a final time. I'm going to say that this u of x and t is the infimum of the integral from t to t plus h of my r, which is called my running cost, plus little u of y of t plus h, h. I want to convince you of why that is. So the infimum over all alphas that are given from t to t plus h, so t and t plus h. And with values in the target A. Okay, so what this principle is saying is this. You start from x at time t. You have many ways in which you can go. And let's say you go and for time little h. Now you explore all these possibilities. And from that ending point, which is called y of t plus h, then you do the best thing. You do the thing that gives you the best final score. So now you do the best. You do the best. Okay. And so now the principle is saying that your best strategy is to look among all these possible things at the one that gives you the best. So what you have to do is you have to sum the cost of this first part of the trajectory plus the optimal cost starting from that new point, y of t plus h at times h. So it's a bit like an induction in time, right? So if you can do the best from today, the best you can do from today is to do the best thing until tomorrow, and from there, do the best thing. That's all there is in that principle of dynamic programming. And I hope you can be convinced of it.
Can I just ask?
Sure.
Is this true for h positive, or is it only true in the limit as h tends to 0?
No, it's true for every h. We're going to want to take it small, but all that matters is that t plus h is less than your final.
Oh, okay, yeah. Mm-hmm.
For every h, stuff like that, but now I'm going to start to make it small.
Mm-hmm. Yeah, thanks.
It's true for every h. That's a good remark. So now, what I'm going to do is I'm going to let h go to 0, and I'm going to do something that's called Taylor expansion. So just some fairly basic calculus. And I'm going to assume that things are regular, smooth enough that I can do this Taylor expansion. So my function u, I'm going to assume it's, you know, C2, let's say. I'm allowed to differentiate. In reality, it's not true. This is a problem. But we're going to do that because that's what we can do for now. Okay, so if I do that, I Taylor expand in h. So I copy what I had. Now the integral from t to t plus h, because h is very small, I can just replace it by h, right, times whatever is in there. And I can take the value at little t, but y at little t, it's x. We start from x. And now this is alpha of little t, right? So I replace my integral by just a value of this at this point multiplied by the width of the interval. And then I add this. Now I want to differentiate in h, right? So I have we need a little bit of multivariable calculus here because u is a function of two variables, space and time. So I'm going to have an h times the time derivative. This is the easiest part, is to differentiate with respect to the second variable. So I differentiate with respect to this guy, this h. And because I can now evaluate this at h equals 0, again, I have y of t, which is, I always use that y of t is x. That's the initial time. I start from time little t at complex. And then I have to worry about my derivative with respect to the first variable. So what I have here is I have a dy ds taken at initial time. So started with gradient of u. And now I can evaluate that at time. Sorry, I made a mistake. This is a t plus h. It's at time t plus h. We have added h to time. This is gradual xt. Okay, but now this guy, we know the law for this. This is the ODE. We know that y dot is f of y and alpha. F at y, but at initial time t, this is at x, not alpha t. Okay, so now I can rewrite this whole thing as the infimum, and the only alpha that matters is alpha of t. So now I can do just alpha in A. And there is an h here. And I have an h. And someone should have told me, I forgot the value at the initial time, so this is 0. So when I differentiate, I should first write the thing at h equals 0 plus the derivatives plus, if you want to correct me, next stuff is little o of h squared. So now I have h. I can factor x alpha plus dtu at xt plus fx alpha dot value plus u, so it's all at xt, plus u at xt plus little o at big O of h squared plus big O of h. You agree? I just Taylor expanded. So what I want to do next is I want to cancel out u of xt from the left-hand side and the right-hand side, because these are on both sides. And I want to divide by h, divide by that. And what I'm left with is 0 equals infimum of alpha in A of r of x alpha plus fx alpha dot value xt. And I can take out this dtu because after all, it doesn't depend on alpha, so I can take it out of the infimum. Okay. So now what I do is I'm claiming that this is a PDE, and you can see it because, well, there is a dtu and there is a gradient. So it's going to be a PDE of first order. It's going to involve just first derivatives in time and first derivatives in space. And to write it properly, I need to define these functions. I'm going to call h of x and p equals, by definition, the infimum over alpha in A of r of x alpha plus f of x alpha dot p. So given a certain vector p, I define h of x and p like this. Now I recognize that this expression is very much of this form, with p chosen to be gradual. So I can write dtu, so now I'm going to take dtu first, plus h of x gradual equals 0. And this is my PDE, and remember, it comes with the final time data. And this happens to be called the Hamilton-Jacobi-Bellman PDE associated to the control problem. Okay, so it always takes this form, a form of a first order equation. This H is called the Hamiltonian. Okay, so it's a first order PDE. This is the kind of PDEs that get solved by things like methods of characteristics, but not so simple really in this case. Okay, so that's good. Now, if you want to, you can do two things with this. One thing is you can solve the PDE. Okay, so this justifies that such PDEs have solutions. Okay, because it's not obvious that such PDEs can be solved. You can represent your solution U as being this infimum of C of xt of alpha with all the constraints that we know. This is a representation on the solution. Can you do this for all Hamilton-Jacobi equations, so all equations of this form? The answer is not quite, because actually the kind of H that I obtained this way, if you look at the definition of H, as a function of P, it's an inf of affine functions, right? This is affine in P. So I can put it here. Affine in P. So here the way I've defined it, an inf of affine function, it's going to be a concave function. So actually you can only get concave functions this way, but you can get all concave functions. If you have non-concave, then you have to work a slightly differently. You have to do more things. In particular, you have to play with two players. I'm not going to get into that. Okay, so this actually helps you solve PDEs. And conversely, we can recover the optimal alpha for the optimal strategy from the solution. If I want to retrace and find the optimal alpha, well, the optimal alpha will have to achieve this inf here. And so I will have to achieve the inf here. And so if I happen to know u, I will be theoretically able to refine alpha. Okay, so at least in theory. By achieving equality in the inf. So you have a correspondence. You see, the game helps you solve the PDE, the PDE helps you solve the game, and this is nice, and we get first order equation. Now, what if we're interested in getting second order equations? So, second order equations, it's long been believed and known that we can do this, but by playing stochastic games. What was above what was something that's called a deterministic game. There's no randomness. You play, you have the controller, you optimize, and that's it. So now we have to play stochastic games. And I mean, I'm just gonna give you 2 examples, which you may know about, and which are related to the Brownian motion. So if you don't know what the Brownian motion is, it's okay, I'm just gonna wave my hands about it anyway. But so the first game you can play is, again, you start from x at time little t. And now you run your Brownian motion. Brownian motion is some complicated process, right, where you move around with the property that what you're doing doesn't depend on the memory of the past. So your direction is not preserved or anything. But okay, you run your Brownian motion, and then the clock rings at time capital T. You arrive there, and you decide that you're going to collect g of y of capital T, a bit like in the other games, right? And so now the u of xt is going to have to be defined as the expectation. So you're going to run this experiment many, many times. It's going to be the expectation over all trajectories that you follow like this, that start from little x at time t of your final time score, g of y at capital T. Okay, and this thing, of course, will come with the final time data, which is g of x. And what is u solving? Well, you may know this. U solves the heat equation. dTu equals Laplace nu. So here it's might be that since you're solving it backwards, you want to have a minus sign, because you're solving it backwards in time. Anyway, so the heat equation with final time data is directly related to Brownian motion. So now you see how you obtain a second order equation. Second order equation. It has two derivatives in U. You know what the Laplacian is, right? Yeah, I'll remind you. Laplacian of U is the sum of second derivative of U. Directions I and I. And so again, you can use this both ways by saying, okay, that means that there exists a solution to this PDE. Not that we didn't know this already, we know how to solve the heat equation, but it's another representation of the solution of the heat equation, like this as an expectation. This is also called Feynman-Katz formula. And conversely, if you know the solution to the heat equation, you know what's going to happen a little bit in your Brownian motion. So to understand what Brownian motion is going to do, you actually have to study the solutions to the heat equation. And you can make the time-independent version, or if you want exit time version. You start from X, you run your Brownian motion until you reach a certain target. That's your target G. And now you decide that big U of X is the expectation starting from X of a certain bonus that you collect at Y of T, which is the exit time thing that belongs to G for the first time. Right, the point of your trajectory that first hits the target. So again, that is going to solve an equation, and the equation now is just Laplace's equation. Laplace's equation with boundary data on capital G, U is little g. Most famous types of PDEs. Okay, so it was believed, you have a question?
Yeah, sorry, could you explain a little bit of why it solves Laplace's equation? Yeah, sorry if I missed that.
I don't know, so that I did not explain, and that's a property of Brownian motion. And I can't explain without going into more probability, but it's you need to go into the properties of the Brownian motion, and this and you can relate it with the mean value formula, for instance. One thing you could do is you can try to do it by hand when by doing a random walk. So instead of doing the Brownian motion, you can jump on the lattice. You know, my square, my grid on my piece of paper here. You can start to do jumps like this. You know, only following your lattice, and that's a random walk. And you can try to apply the same type of Taylor's expansion that I was doing here for this type of motion. So you say, okay, now I take my first step. I look at all my first steps plus then I take my expectation. And so when you do that, you're going to average, since you take an expectation, you're going to average over all the neighbors, the neighboring point of your thing. And when you take a function and you Taylor expand and you average over all directions, the first derivatives cancel and you get only the Laplacian. So this is what you can get from a formal Taylor expansion. Then you have to convince yourself that the random walk is a good approximation of the Brownian motion that eventually converges to Brownian motion. But so this is roughly the idea, is that when you Taylor expand a function, because you have to average uniformly over all directions around your centering points, you will pick up a Laplacian.
Yeah, thank you.
I was not intending on saying much more than that.
Yeah, thanks.
But this is something that's very classical, very standard. Sort of basics of probability. So now less standard is what I'm going to tell you now, because for a long time it was believed that if you want to get a second order equation, you have to have a stochastic problem, like this one in motion. And Paul and Carroll, the Paul and Carroll game gives an example of a deterministic game for which the solution is also second order. So it's deterministic, but it still has a second order PDE associated. And after, so this was shown by Kohn and myself. And after that, we also did another work where we cooked up a more general game. Exists to treat any reasonable second order game generally exists for any second order equation. So it has to have some property. It has to be elliptic or parabolic. So elliptic or parabolic are things that resemble Laplacian or the heat equation, but a bit more general. Right? So Laplacian U equals F is a model case of an elliptic equation. The heat equation is the model case of a parabolic equation, but there is a broader class, and for this whole class we can find deterministic two-player game that works to approximate the equation. So the main point is that you have two players instead of one, and then you also have this epsilon. You have this asymptotic of epsilon going to 0. You remember epsilon was the step size in my original Paul and Carroll game, right? So take steps of size epsilon. Okay, so now it's time to give you the answer to the solution to the Paul Carroll game. And so if you want to exit, what you have to do. It's not so obvious to guess if you just try. It's easier first to try it in a disk. I would recommend first trying it. Okay, let me give you the answer. The way of thinking is a little bit like what we've seen in the principle of dynamic programming, is you want to think of the end of the game. What is the last step? And then you can backtrack from there. So think of the last step. You're near the boundary, and assuming that Paul has found his way to near the boundary. Okay, he's there, or the game is there. When can you exit? Well, Paul can try to go sort of like that, but there's no hope that this is gonna work, because Carroll is always going to do her best to oppose him. So no. It is much smarter from Paul's point of view to go sideways, because now if he does this, even if it gets reversed, he's still out. So in fact, the points from which Paul is sure to exit are all those points that are such that if I draw a segment of size 2 epsilon centered at this point and such that the endpoints are both outside, then that point is a point from which Paul can exit. Okay, then he just has to pick one vector, and then it's irrelevant which one he picks, because whether Carroll reverses it or not. Okay, so now what I do is I take all these segments of length 2 epsilon and I make them join 2 points of the boundary. Right, so something like this, and this creates a little layer. Now we're gonna get a layer. So I join all these points together. It's a bit delicate, but something like that. It creates a layer, and from anywhere outside of this red curve, I am sure to exit if I'm Paul. And now you just have to repeat. So how can you be sure to exit in 2 steps? Well, if you're in the second layer, built from this first layer, and then in 3 steps, third layer, etc. So by drawing these layers and layers, you can find that actually you can exit from any point. The number of steps it will take you will depend on which layer you sit on. So one remark is Paul cannot exit in the parts of the boundary that are negatively curved like this one. You see, because if you're here, if you draw these segments, you don't exit. You can only exit from the part of the boundary that's actually positively curved. And what happens when you draw these layers, and you'll see that these curves eventually reach, you know, they come and they eventually reach the whole set. But it's the curvature that's allowing to make progress, because if we had a flat boundary, there's no way to ever exit. Okay, so it's just thanks to the curvature of the boundary that there is a little progress in this propagation of these fronts. Now you can think of these things as fronts. Okay, and now let's try to do the principle of dynamic programming again. So I'm going to do it in the thing where I have the horizon time, just to show you it's a similar thing. So u of xt, this is going to be the minimum. Okay, so Paul, what does he do? He chooses a vector of norm 1. And what does Carroll do? She chooses this plus minus 1 number. Now my claim is that you have to represent this as a min-max, because for Paul, he's trying to do the minimum. He's trying to reach a certain minimum. But Carroll is trying to make it a maximum. And because Paul has to announce his choice before Carroll, he has to anticipate for the max. He has to take the mean over all the possible max. Whereas if Carroll was choosing first, it would be a max of a min. But now it's a min of a max because he has to anticipate for this worst case scenario. And now what do? You do the thing that starts from new step epsilon dv at time t plus, what do we do for time? We have to make one increment of time to be epsilon squared. So one step equals time epsilon squared. That's the best way to scale it to match epsilon size of the vector, and you'll see how it works. So this is the thing starting from after my new step, and then what have I paid along the way? I just paid the price of oh, I've paid nothing. Okay, so he's trying to collect a score. You know, in this version, he's trying to collect a final score. So it's not really exit, it's final score, u of x capital T equals g. So the best thing he can do is to first make his best first step and then collect the best. Okay, now you can start to do the Taylor expansion. Epsilon going to 0. And you get this u of x of t equals min max. Now I expand properly, so better than what I did earlier. I should start at the value for epsilon equals 0. Plus I should add epsilon dv dot the gradient of u at x t plus dtu plus epsilon squared dtu at xt plus little o of epsilon squared. And now I need to go, in fact, to little o of epsilon squared, so I have to add my second derivatives. So I'm going to have the Hessian, you know, the Hessian of u at xt in the direction. This is like my scalar product, if you see what I mean. Okay, so I expanded my u, I Taylor expanded, but what I did is because I know that things are going to happen at order 2, because I'm smart, I know that I should already expand to order 2 and then put my little o's. Okay. So what happens in this term? Okay, you think you have fixed term, so the u's they cancel. And now I get an epsilon term. So if I want to minimize, maximize, this is the dominant thing. You want to min-max this thing because the rest is smaller. It's epsilon squared. Epsilon squared is smaller than epsilon. Okay, so now you min-max. Min-max. Norm 1. Epsilon BV. What is that? So first you max over B. You have a plus or minus 1. So when I max, what it does, it takes the absolute value. It's the number. So the max is the absolute value. I can delete that. And now what is the mean? Well, the mean of that, I claim this is 0. What do? I just have to choose a vector V that's perpendicular to grad U and norm 1. So let me write it like this: grad U perpendicular divided by its norm to make it norm 1. Okay, you will tell me, okay, but what if grad U vanishes? Then I cannot do this, but if grad U vanishes, it's okay because that term is 0 anyway, so I don't have to. Okay, so typically that's the choice you have to make. V equals grad per Q. Okay, and now you replace that choice into here, and you obtain 0 equals. There is no other choice to make, so that term has now disappeared. This thing now is 0. This min max, and the only thing that remains is this epsilon squared over 2 d2u. So the BV, because it's a quadratic function here, I don't need to care about plus or minus 1. I just need to care about in-plugging this guy. Okay, and now I have a dtu. And because I have an epsilon squared, that's in factor, I'm gonna just do it like that. The epsilon squared, I divide by it and by literal of epsilon squared. So in fact, what is true is that my function, I should have called it u epsilon at the beginning. It depends on epsilon. And what is true, it converges as epsilon goes to 0 to u that solves this PD. That's the formal PD that I get when I let epsilon go to 0. So all of this is a little bit formal. If you want to make a proof with that, you actually need to work a bit more because these Taylor expansions are not completely rigorous because of the lack of C2 regularity of the solution. So to do this properly, you have to use the theory of viscosity solutions initiated by Crandall, Lyons, and others, and others in the 80s. And that allows you to actually give a meaning to the formal Taylor expansion. So what PD have I obtained here? This is a PD that's called mean curvature flow. So it's a second order PDE. You can recognize it's second order because it has some second derivative in there. It is a kind of elliptic PDE, but it's a very particular kind. It's called the geometric PDE. And what it is telling you is that the fronts that I was drawing at the beginning, they move by mean curvature. So in other words, the velocity of these fronts is proportional to the mean curvature of the front at the point at which you're moving. And that's why it's called mean curvature flow. It is well studied on its own. And it allows you to refine the optimal strategy for Paul because once you know this function u, what Paul has to do is choose this. That's the strategy. So what he should do is he should take the tangential vector to the level set. So you should look at all these level sets, take the tangential. Okay, so this is pretty much what I wanted to tell you, that you can have second order PDs by playing these types of games. And I wanted to come back to the very beginning game because I forgot. This exit time game, when you write the Hamilton-Jacobi equation that's associated with it. Exit time game. This h of grad u equals 0. This guy is just the norm of grad. So for the game without time, the exit time game is just a solution to this guy, this solution, this equation. That is called the Acornal equation. Acornal, like you know, in Greek, icon means the ray of light. So because it's the trajectory that's followed by straight rays. And what is the solution that we've seen? U equals distance from x to the boundary, right? That's what we've seen. And that actually does solve this equation. Size of the gradient of a distance function is 1. Okay, but if you think of this equation, you will see it has many, many solutions. So let's think of it in 1D. And let's say you want to take it 0 on the boundary because the exit time at the boundary is 0. So I have my distance to the boundary, the graph is this. You observe that it has a singularity in the middle, so already it's not good for regularity. I told you there is no regularity, and it's true. But now let's look at these. We can make another solution like this. Anything whose derivative are plus or minus 1 is going to solve that. Right, because in 1D, this is just u prime equals 1. And now you can make this thing, you can move these, make as many bumps, you can make them like this. Okay, so there's infinitely many solutions to that equation. Not good. We don't like that. We don't like solutions, equations that are infinitely many. However, for my exit time, I know that it shouldn't be this guy, it should be this guy. The exit time is this, it's not this. So what's the difference? Well, the point is that there is a unique good solution. There's only one that's actually the correct one, and that is called the viscosity solution. So viscosity solutions theory selects for you the one correct solution, no problem, which is the one that you're achieving and solving, not these other sort of crappy ones. And in order to see how to get that viscosity solution, I invite you to do the following. To add to your problem a little epsilon perturbation, add a second order term that's going to regularize your problem. Now you have a good ODE. This thing is like lower order. For each epsilon, you have a unique solution by Cauchy-Lipschitz theory of ODEs. And when you do that, it's going to, instead of taking a solution like that, it's gonna round off the corner. This guy now is going to have a corner that's rounded off at scale epsilon. And as epsilon goes to 0, it will converge. It will converge to a solution of that, but it will converge to the correct one. You will not see those. You will only see, when you round off the corners, you will only see the correct one in the limit, and that's the viscosity solution. So it's time to stop. If you have any questions, go ahead.
Yeah, thanks a lot. Yeah, it's really interesting. Yeah, does anyone have any questions?
Yeah, maybe a short one. I'm curious what the combinatorics problem was that this very fun game came from. Oh, thank you for the wonderful talk, by the way, before I even start. Yeah.
Thank you. Okay, so I can tell you just a little bit about what I understand because it's not my expertise topic, but he just wanted to, his domain was the square, right? And he was asking, when you sum vectors of size 1, and you sum them with a plus or minus sign, so pi is of size 1, and you don't know what the signs are going to be, so that's why you have to plan for this max or blah. When can you be sure that the size of that vector is going to be bigger than some given number r? And the size of that, so I'm really talking about the size of that vector that makes the sum of these vectors. And this size, it's measured in this L infinity norm. So the norm being, you know, if you have a vector x, y, the L infinity norm is just the max of x and y. So having L infinity norm bigger than R just means precisely escaping the square of size R. And so you have this with inequality like that is equivalent to saying you're in the square. So what he wants is to be outside of the square. So he starts from the origin. In fact, his game is starting from the origin. Can you escape that square? And the vectors were of norm 1, but R was very large. So of course you can zoom everything down to make the square have size 1 and the vectors be small. It's equivalent. So he was asking, as R gets very large, what is the number of vectors I need to add in order to be able to guarantee this condition? And that's exactly how many steps you need to make in that game in order to execute.
Okay, thank you. Maybe a short follow-up. How does this change massively if you go up high in dimension? Isn't it most efficient to stay in one plane? Or is it better to
So
plane?
if you go to high dimensions, to 3D, for instance, you can play that same game, but it's not going to give you the same equation. So it depends what equation you want to reach or you want to model, if you want. So one way would be that Paul picks a vector, but then Carroll can take one way would be that Paul picks a plane and then Carroll picks a vector on the unit circle of that plane.
Okay. Yeah.
Another way that it turns out to be good is to pick a cross. Paul picks a cross like that, like a frame, if you want.
Mm-hmm.
And she picks which of the 4 endpoints of the cross. And that gives you mean curvature. Because you know the mean curvature is what you get when you sum the principal curvatures. Gives you a mean curvature. Or you pick a vector and then she can reverse. And that gives you, so one of them, if you just pick a vector, I think you get motion by the minimal principal curvature, the smallest of the principal curvatures. If you pick the plane, you get the max of the principal curvatures. And if you pick the cross, you get the average of the principal. Yeah. So it's your choice.
Okay, thank you very much. Cool stuff.
So, okay, is there a reason to think the solution to the limiting PDE for a Poincaré game is not in fact C2? Yes, so very good question. So in the second order equations, it is true that you're not going to encounter these rough mountains like in the first order equations. Those solutions may be C2, but they are not always, so it depends. So for instance, if I take a domain like this and I look at the exit time for that domain, you remember that you cannot exit from this part, right? So if you were to draw the graph of the solution exit time function, it would the graph would be here glued to 0, then it would come in a nice smooth way, but then it would have a cliff, like a real vertical part as you approach this part, because the exit time there would be actually strictly positive, even though you're at the boundary. So it's an example where you would have a discontinuity at the boundary. And so proving that these things are C2 is actually hard. So it's easier to apply the viscosity solution framework, which does not require any regularity. And then if you want, a posteriori, you can try to prove that your solution is classical and is smooth, but it's not always the case, and it's not always easy. And in the case of this Poincaré game, we actually proved it by hand that the solution is C3, and it was quite a bit of work. So just to say that this regularity question is delicate. So even though it is regular in most cases, it's not something. So I see there was another question.
Ulrich had a question.
Yeah, I have a question, or rather a comment. The thing you said at the end of your talk about identifying the unique good solution reminds me very much of a method called total variation diminishing methods in the numerical computation of solutions of modeling shocks or discontinuities, say in fluid dynamics or so, because if you solve or if you model discontinuities, you actually have multiple solutions as well, but only one is entropy satisfying, and that one is identified by minimizing the total variation, which is a procedure which is very similar to what you demonstrated at the end when you showed that the good solution is just a triangle. I wonder, is that just coincidental, or is there possibly a more systematic relation to fluid or disk shock modeling in fluid dynamics?
I think it's not exactly the same thing. So there is this notion of entropy solutions. Indeed, whenever you have shocks, they select one admissible shock that's physical. But I think viscosity solutions is a different thing, even though there's some analogy. It's not the same phenomenon as. Okay, I'm a little exaggerating, because it's true that when you take this type of Acornal equations or Hamilton-Jacobi equations, you also have shocks in the sense that you have characteristics which cross. And so you have to select which one of those characteristics you have to see. So it is more similar than what I was saying. But,
okay, thanks.
But yeah, there are some subtleties, but it's definitely the same flavor, I would say. But I want to answer, there was another question here that was a good question about the Taylor expansion. So here, the point is that we have scaled time. We have chosen the unit of time to be epsilon squared because we anticipate that we're going to get the second order solution. So if we put a unit of time to be epsilon, we'd have an epsilon here. And that would be now the leading order problem. It would not be interesting. So because we want to get the PDE at the end, we want this term and this term to come with the same factor in front. And we could expand to higher order in time if we wanted, but that would only give us epsilon 4 now, because time has been scaled like that. So if you expand to higher order, you're going to get epsilon 4, and these terms are not relevant, not interesting. So the leading order that's relevant here is going to be epsilon squared, and so you sort of tailor it. Your choice of time step is cooked in to fit exactly what happens on the space side.
Yeah, I had a question as well. So in the Paul and Carroll game, it's where we can see kind of from first principles what the best strategy is. Can this kind of thing be useful for solving PDEs if we can reconstruct a game from a PDE?
Yes, you're absolutely right. In the Paul Carroll game, you can solve everything by hand, and you can make what's called a verification argument, which is like the old-fashioned way of doing those things before viscosity solutions were invented, was to actually design the strategy. You guess the solution, like this distance function. You design your strategy based on it, and then you check that it's actually optimal, etc. And this you can use. And in particular, what has been done this way is that I told you that you cannot exit from the negatively curved part here. And so the motion that's happening in this problem, this exit time, it's not quite that you're moving the front by mean curvature, but you're moving by positive part of the mean curvature. Okay, so it's only the positive part of the mean curvature that moves. And thanks to this game, we were able to prove that positive mean curvature flow has a waiting time. So it takes a while for the things to start moving on this negatively curved part. And that was not something that was directly accessible from the PDE. So if you looked at the PDE, it was not clear that it was going to have this positive waiting time here, but if you look at it from the point of view of the game, it's more clear. So this was one instance where the game was able to solve a PDE. And I can tell you another game if you have a minute.
Yeah.
It was also quite, got a lot of attention in the probability and PDE community, not so old, also like 15, 20 years ago. Around the same time as Paul and Carroll. It was a game of tug of war, it's called, by Perez, Schramm, Sheffield, and Wilson. Perez, Schramm, so 4 pretty well-known probabilists. And so the game, it's a bit like Paul Carroll. You start from a place and you have 2 players that are opposing. And now you flip a coin to know who makes the move, who decides on the move. Okay, so you have a coin, you flip. The player that gets the choice picks a vector of norm 1, okay, or epsilon, just like before. Epsilon. And then you flip a coin again and you say, okay, who gets to choose next? You decide if the game moves again here or there or there. So the idea is that you want to collect a premium at the boundary. Right? One player wants to maximize, one player wants to minimize. So let's say here it's bigger than there, for instance. So one player is going to want to push this way, and the other player is going to want to push that way. But so it's going to, of course, alternate between those two. And you can do exactly the same thing with a value function. It's going to be the expectation over your coin flip of u of x plus epsilon v. You do the same, you Taylor expand, and because now you have to do this this coin flip, it's going to also give you a second order equation. That equation is called infinity Laplacian, so it's almost like the one we had before, but instead of grad perp u, it's grad u. And then you're going to solve this equation. It's called infinity Laplacian, denoted by this. And now what's really interesting is that this equation, from a PDE standpoint, is not easy to study. It's not easy to prove existence of solution. It's not easy to prove that solutions have this regularity or that one, that their solutions are unique and blah. And thanks to this game interpretation, they were able to actually answer these questions on that PDE. So it's very closely related, but since I had not enough time, I didn't mention it, but now it's a good time to say. So sometimes when you're lucky, you can get new information about the PDE, but not always.
Yeah, thank you. Yeah, that's really cool.
Yeah, so look up this tug of war. It's very easy to understand, and it's very easy to make the principle of dynamic programming and this formal Taylor expansion. It takes 2 time.
Yeah, thank you.
I have a question. So, you know the solutions that were discarded by the sort of viscosity solution method, do those correspond to any games? And if they do, then if you were to sort of apply the viscosity solution method to those games, then would you not get those solutions? And I suppose what I'm trying to get at is that why do you want to add like a perturbation of the form epsilon u double prime instead of just any other perturbation that you might add?
It's a good question. The reason why I added this epsilon u double prime is because that's one way of getting viscosity solutions that's easy to describe. However, there is another definition which doesn't involve that and which is more appropriate for games. And you can prove that they coincide. These are the same solutions. And so the bottom line is when you start from a game, you will only get the viscosity solution. You will not get the other guys. And the reason is not really because of this epsilon u double prime that's hidden there. It's not there, but there is another way of looking at it by a maximum principle that I can't explain. It would take too long, but from the other definition of viscosity solutions, you see that that's what you need to do.
Okay, so is there really no way of getting games with the other sort of solutions as solutions?
Not these types of games, no.
Okay.
These games are always associated to something that satisfies what's called the maximum principle. Maximum principle is like a comparison, saying, if you know that you start with a bigger, your score is bigger, for example, your initial condition is bigger, then the solution to your game is going to have to be bigger. That's what's called the maximum principle.
Okay.
And so you have to have that in these types of games, and so it will give you a viscosity solution.
Okay. Thank you very much, and thank you for your talk overall. It was very interesting.
You're welcome.
Any other questions? Right, well, if no one else has any questions, I think we should all thank the speaker once again. It was really interesting. Yeah, so thanks a lot, Professor Serfaty.
Thank you. Good luck with your studies.
Yeah, and yeah, thank you to everyone for coming. Yeah, hope everyone has a good Easter break.